Lecture 27. So we were doing the maxima and minima part. So we've done the local maxima and local minima. Now we'll be talking about absolute maxima and absolute minima. So the first point is absolute maxima and minima can be achieved over a closed boundary, right? We'll have a boundary, we'll have a closed and bounded region over which we'll be talking about the maxima and minima. So how it is different from the problem which we were doing in last two lectures, that we're gonna discuss, right? So first of all, the main theoretical difference is what? So I'll be discussing that theoretical difference after discussing one example. So first we'll straightforwardly start from an example of absolute maxima and absolute minima, and then we'll be talking about the striking differences between that problem of local maxima and minima and absolute maxima and minima, right? So let's say I'll start from example. So this is an example which is in the book. So idea is find the absolute maxima and minimum values. Of course, we'll be talking about values along with the points of f of xy is equal to 2 plus 2x plus 2y minus x square minus y square on the triangular plate in the first quadrant. Bounded by the lines x is equal to 0, y is equal to 0, and y is equal to 9 minus x, right? So let's say you have a 3D figure, right? So this is your x, this is your y, and this is your z. We've given that x is equal to 0, y is equal to 0, and y is equal to 9 minus x. So in other words, I can translate it as x plus y is equal to 9, right?
Yes, sir.
So what is x is equal to 0?
So it's equal
Y
to
axis.
y-axis. Y-axis.
Y-axis, simply y-axis, right? So this is our y-axis. Let's we extend it. Okay. So this is our y-axis and this is our x-axis. But we have also, there is one more information, that is what only in the first quadrant. So these are the information which we're gonna construct. One is first quadrant, another is x0, y0. So these are the x0 and the y0, right? And if we talk about x plus y is equal to 9, so that means, let's say this is the point over here and this is the point over here. So this point is, let's say 3 0, and this is 0 3, right? So our line would be like this, right?
9 0 and 0 9.
Sorry, yeah, sorry, thanks for the correction. So I'll put it again. So it should be 9 0 and 0 9. Yes, fine, fair enough. Okay, so what would be the reason on that? So this is the reason. Is it okay? This triangular region is our region of analysis. Okay, so what
Yes,
is
sir.
that? This is the part
Yes,
of the
sir.
so this function, this is a function. Of course, it will give you x versus x, y will be the inputs and z will be the output. My idea is, let's say we have something and some surface, and that is what, let's say anything f of x is equal to y. Sorry, f of xy. So that's what it takes the input from here, 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 and we see Z as height, right? Is it okay? But if I talk about only this region, so I'll be having the image along this region only, right? Is it right?
Yes, sir.
Are you with me on this? So in this region, if I'm getting the maxima, there would be a maxima. If I'm getting the minima, there would be a minima, right? So basically, here domain will be our main focus. Why? Because that domain is actually a subset of the whole domain. So we'll have a closed region over here. So we'll be talking about only that particular closed region on which we'll say that f of x, y's are getting some kind of values. So how we do this question? So let's start with this. So first of all, we'll take our f of xy as it is. So that means our f of xy is 2 plus 2x plus 2y minus x square minus y square. Okay, so we'll be saying that f of x, we'll be first calculating those equations. F of x, that means the partial derivative with respect to x, that would be 2 minus 2x. And what would be fy? 2 minus 2y. So we'll equate them to 0 and we'll get the values of x and y. So that is what? 1 minus x is equal to 0 and 1 minus y is equal to 0, which implies x1 and which implies y is equal to 1. So our critical point is 1, 1. Right? So we'll find the value at 1, 1. Directly we'll be finding the value at 1, 1. So you put that point over here. So of course, this will cancel this and we are left with this. So we'll keep tracking these values. So first of all, I'll mark this value, and this is something which we have got at 1, 1. F11 is 4. Right. So now we'll be separately dealing with those boundaries which we have marked, which are given to us. So let's say draw it over here. So these are the boundaries, right? So I'm only constructing the domain part over here, right? That's why I'm taking the 2D picture of. So this is your 0, 9. This is your 9, 0. And this is your 0, 0. So can you tell me what are the boundaries? Can anybody tell me what are the boundaries?
0, 9, 0, 0.
Yeah.
Zero.
Y0, X0, and X plus Y is
X
equal
plus
to
y equals to 9.
Right. So we'll be dealing with the boundaries, right, by one, right? So very first we have the boundary y is equal to 0. That means, let's say we call it as O, this A and this B. Boundary along OA. Is it fine? So what will happen if I put y is equal to 0? See, y is equal to 0 will serve as a restriction to this function. So if I put y is equal to 0, of course, this function will behave 2 plus 2x plus 2 times the 0 minus x square minus 0. So this function would be in one variable. Am I right in saying this?
Yes, sir.
Right?
Yes, sir.
Why? Because I am my points, all the points are on OA, and OA have some kind of feature, and that feature is what? It keeps the y always 0, right? Because we are walking along the x-axis, so we know that we'll not move in y direction, we'll keep ourselves to the x direction. So that's why we can restrict y to be 0. So what is the advantage of doing this? Now your function will become a function which is just a function of one variable. Is it okay? So if the function is in one variable, you can always talk about the maxima and minima. It's pretty much easy, right? So how we do it? So Can you tell me how we do it?
So we have to differentiate the function and equate it to
Exactly.
0.
Exactly.
Yes, sir.
So let me, if I say it, let's f dash at x0. So this will be 2 minus 2x, which is equal to 0. So that means x is equal to 1. So along this line, y is always 0. So it becomes what? 2 plus 2 minus 1. So that means 3. So I have f of 1, 0 is equal to 3. Okay. But I'll be dealing with the corner points separately. That means this point and this point. So f0, 0 would be what? 2. Right? And what would be f90? And that would be what? f90. This is your 90. So you put
61.
so you put 9 over here. So this becomes what? 2 plus 18 minus 81.
Minus 61.
Minus 61.
So f of 90 will be minus 61. So let's again mark those points. So which we got, right? So we have already marked this point f11. So let's mark this one and this one and this one. Okay. So that's how we dealt with the one boundary. So let's go to the next boundary.
सर
Yes.
सर जो हमने स्टार्टिंग में x प्लस वाई इक्वल टू 9 लिया है सर वो
हाँ।
मतलब क्वेश्चन के अंदर ही आएगा ना
आ
तो
रहे हैं
उसको
हम, उसके ऊपर भी आ रहे हैं.
ओके
ठीक
सर
है, उसके ऊपर भी आ रहे हैं. So in second boundary x is equal to 0. Okay, so we have second boundary which is what? X is equal to 0. So I'll put x is equal to 0 in this function. So more precisely in this function where we have already put y is equal to 0. So let's say put x is equal to 0 over here. So it becomes what? F of 0y, right? So if you put x0, so that means what? 2 plus 2y minus y square. Is it okay? Is it fine?
Yes, sir.
Now, this is again a new function, but having this kind of same characteristic that this is a function which is in one variable. So if we want to compute the maxima and minima, so we'll take simply derivative. That becomes what? 2 minus 2y, and we'll keep it to 0. So y will be 1. So our point will become 0, 1. So f of 0, 1 would be 2 plus 2 minus 1. So 3. So f of 0, 1 is 3. So let's mark this. And again, we'll be dealing with the boundary points separately. So this is our boundary point, this and this. So we know that f of 0, 0 will give you the same value. You can calculate it if you want. F of 0, 0 from here. So it becomes what? 2, right? And what about f of 0, 9? So let's calculate it. F0, 9. Again, it will give you a similar value. 18 minus 81. So this becomes
Minus
what?
61.
Minus 61. This is your F0, 9. So let's mark again these two things. Now we are left only with the one boundary, and that boundary is what? That boundary is x plus y is equal to 9. Okay, so again we have a kind of restriction. So our third boundary is, so these are constrained precisely, we say that. So x plus y is equal to 9. So it's a kind of constraint. That means it's a kind of rule. Every linear equation is a kind of rule. Every equation is a rule, right? So if you say this, x plus y is equal to 9, what does it precisely means? If you want to explain it worse, that means sum of abscissa and ordinate should be equal to 9. That is the rule. Okay. So that means your y and x has a sort of connection. That's what your y will be always 9 minus the x. That means your ordinate will be always equal to 9 minus abscissa, right? So this rule again will be put over here. Okay, so this becomes what? Again, you replace your y by 9 minus x. So your equation will be only in x. Okay, are you getting this?
Yes, sir.
Okay, so now you see that this becomes what? 2 plus 2x plus 18 minus 2x minus x square minus 81 minus x square minus 18 plus 18x. Okay, so this will get cancelled, 2x and 2x, right? So we are left with minus 2x square plus 18x minus 61. So this is our kind of one variable. So again, let's talk about f dash plus 18, right? So we'll put it equal to 0. So x will become 18 by 4, 9 by 2. So if your x is 9 by 2, you know that y is 9 minus x. That means 9 minus 9 by 2, that is 9 by 2. Right? So now we can get the value at this function. So that means f of 9 by 2, 9 by 2. That means, so we put, actually we can put directly 9 by 2 in this function as such, if you really want. So if you put this x 9 by 2, y 9 by 2, that means here, so 2 plus 2 times 9 by 2 plus 2 times 9 by 2 plus, sorry, minus 9 by 2 square minus 9 by 2 square. So this becomes, right, 18 and 18, 20 minus 81 by 4 minus 81 by 4. So 20 minus 81 by 2 to 40 minus 81 by 2. This becomes minus 40 by 41 by 2. Is it okay? Are you with me on this?
Yes,
Right?
sir.
Yes, sir.
So your f of 9 by 2 and 9 by 2 is this. Fine?
Yes, sir.
So let's mark this one. Right? So can you see what is the maximum value which we have achieved? So you have the minima, that is minus 61. Okay. And what is your maxima? Can anybody tell? This is your maxima. 4. Right? So you say that finally, what will you say? Your maxima is at 1, 1. And what is your maximum value? Maximum value is 4. And minima, what is your minima? Minima is at 2 points, 90 and 0.
0,9
And minimum value is what?
minus 61.
A1.
So that's the complete question. Okay. Now we say that why we did this. I mean, precisely why, the same, why the particular method has been adopted. So we've already said that, getting the local maxima and minima, you need the interior points. Okay. So I guess I've already discussed about the interior points. Let me talk about the interior points again. So again, I'll not go into the precise mathematical form. So I'll try to make you understand through the pictures only. Okay. So let's say this is your 3D graph, right? And this is, let's say, your z is equal to f of xy. So point is, if you're talking about the maxima and minima, let's say this point is your minima, or this point is your local minima. So this can be described only on interior points. So what point is an interior point? Let's say this is the domain, or domain may be whole R2, whole xy plane. Okay, so a point is said to be an interior point if you draw, if there should exist a there must exist a small circular disk, so that when you draw a disk along this point, considering this point as center of the disk, this disk should completely contain in this domain. Is it okay? Right? Are you getting this? Is it fine?
Yes,
Yes,
sir.
sir.
Okay, so no matter how much small the disk is, so let's say this point, is this point an interior point?
Yes, sir.
Yes.
Why? Because you can still draw a very small, very small, it's just the limitation of this marker. Otherwise you can draw, not that much limitation. Let's say this one. Okay, this is still an interior point, right?
Yes, sir.
No matter how small circular disk you may, you can draw, and the disk should completely be the part of the domain. It should completely lie in the domain. But this cannot be an interior point. Why is it so?
It is a boundary
Lies on
point.
the
It's a
boundary.
boundary.
Yes, it's a boundary point. So what is the specialty of the boundary point? No matter how small you draw a disk around this, okay? Let's say you draw a very small disk around this, or let's say you draw a bigger disk will again a problem. But if you draw a very small disk around this point, okay, let's say a smaller one. But even then, what do you get? This disk cannot completely lie in the domain, right? Small
Yes,
part,
sir.
even a small part will lie the outside. That means disk will contain points from outside the, what you say, outside the boundary, right? And inside the boundary as well. So this point has to be what? This point would be a boundary point, right? But on the contrary, this point cannot be a boundary point, right? Because you have always a disk which will not get the points from the domain, right? If you draw a small disk around this disk will not contain points from the domain. See, so what I should say, let me make it more clear. So interior point means what? Interior point means what? That a point is said to be an interior point. Interior point of n, right? Let's say this, this amoeba shape is n. If, and this point, let's say I name this point as AB, P point. A point P is said to be an interior point of n if there exists a small, I would say there exists a disk with center AB or P with radius R, no matters how small. कितनी भी छोटी हो फर्क नहीं पड़ेगा, ठीक है? कितना भी छोटा उसका रेडियस हो कोई फर्क नहीं पड़ेगा, जैसे ये हमने यहां बनाई थी छोटी सी. तो no matters how small, such that disk should completely lie in n, right? So the most important words are what in this definition? Disk should completely lie in n. And secondly, no matters how much small that disk is. Okay, so I'm not saying that every disk should lie this. Every disk तो possible ही नहीं है. देखो, सोचो अगर मैं इसके अराउंड, अगर मैं इस पॉइंट के अराउंड इतनी बड़ी डिस्क बना दूं, तो ये सारी डिस्क थोड़ी n में चली जाएगी, जाएगी नहीं ना? समझ आ रही है मेरी बात?
Yes,
बोलो।
sir.
Yes, sir.
एक डिस्क मिल जानी चाहिए बस, वो चाहे कितनी भी छोटी क्यों ना हो जाए, जैसे यहाँ एक मिल गई, सो यू गेट वन डिस्क, योर जॉब इज डन. So that means you can call that point. Now that point, that P point AB, now it is, it qualifies to be called as an interior point of N. Is it okay? So it would be interior point of N. And what is the boundary point? Can you tell me what is the boundary point? Yes. Anybody? Anybody wishes to define the boundary point? This is your boundary point. Bolo. P
So the
dash.
boundary point is a point which, मतलब,
जिसको
uh,
माने और
is
एक
it
डिस्क राउंड करें तो क्या होना चाहिए?
No matter how small the radius is, it always
always lies outside the domain of the.
हाँ,
outside
लेकिन
the
इसमें एक डिस्क नहीं चाहिए, इसमें सारी डिस्क, किसी भी डिस्क ड्रॉ कर लो, सारी की सारी डिस्क सेट से भी पॉइंट उठाएंगी और सेट के बाहर से भी पॉइंट उठाएंगी. इज इट ओके?
Yes, sir.
Right? So we'll say that. See, that is the major difference. Here we say that there should be at least one disk. बस एक हो जाए बात खत्म. यहाँ लेकिन हम यहाँ क्या बोलेंगे? Every disk. Boundary point की कंडीशन में क्या बोलेंगे? Every disk, right? So a point P dash CD is said to be the boundary point of N if every disk, there exists one nahi, every disk centered at CD, P dash CD should contain points from set N as well as outside the set. Is it okay? Right? So what are the important points of this definition? Every disk. ठीक है ना? Are you getting this?
Yes, sir.
And here I'm saying what? Should contain points from the set as well as outside the set. ठीक है? Right? Yes. Are you getting this?
Yes, sir.
Yes, sir.
See why we are dealing these problems in this way. So let's come to that point. So I was saying this thing. So here you have seen that we have only this part of the domain, right? यही है ना, blue वाला. Is it okay? You getting my voice?
Yes, sir.
Yes, sir.
So
Yes,
what
sir.
I'm saying is this blue part is your interior points. It contains only interior points. Okay. So while dealing with the interior points, we are using our strategy that f of x should be equal to 0 and f of y is equal to 0. And then we'll be calculating that maxima and minima. But when you don't have interior points, so you have this blue line, right? So at blue line, your every point is what? Boundary point. Okay. So you cannot apply that local maxima and minima techniques because it only works for the interior point. So for boundary points, that's why we consider the boundary separately and we try to find the maxima and minima using that using that single variable derivative test. Is it fine?
Yes, sir.
Are you with me on this?
Yes, sir.
Okay, so you got the idea that why why in this particular way we are doing that question. Okay.
Yes, sir.
So I mean, we may try one more questions if you want from the exercise. Question number 31. So f of xy is given to us. (2x square minus 4x plus y square minus 4y plus 1). and we have those boundaries. That means x0, y2, and y is equal to 2x. So you should draw it, but you should try to draw only boundaries, not the function itself. Okay. So just try to draw the boundaries in 2D. That's it. That's more than the sufficient. Okay. So x0 again means what? Y-axis, and y is equal to 2. So that would be a horizontal line, right? Y is equal to 2. And y is equal to 2x. That's what? So that is somewhere here. Okay. Let me make it more clear. Yeah, that's it. So is it okay?
Yes, sir.
क्योंकि देखो अगर x को 1 पुट करोगे तभी y2 आएगा ना, तो ये वाला पॉइंट क्या बन जाएगा? पॉइंट ऑफ इंटरसेक्शन 1 2 ही बनेगा ना ये वाला पॉइंट.
Yes, sir.
Yes, sir.
ठीक है. सो आई मीन ऑफ कोर्स ये लाइन नीचे भी है, लेकिन विल बी ओनली कंसिडरिंग दैट रीजन बाउंडेड बाय these line. That means y is equal to 2, x is equal to 0, and y is equal to 2x. So the region encloses these boundaries would be what? Only this region. Yes?
Yes, sir.
Okay. Right? So this is the region of consideration. So of course we have few boundary points with us, and that boundary points are what? So this is 0, 0, and this is 0, 2. Is it okay? So let's try first with for local maxima and local minima. That means we'll be talking only about interior points, points which are interior to this disk. So how we do it? We'll simply calculate fx and fy, and we'll keep them to 0. So fx would be what? 4x minus 4. That's it. And what is your fy? That is 2y minus 4. That's it. So your x is 1 and your y is 2. So we get the same point. That means same as the corner, f12. So let's get that f12. So of course we'll put that value over here. 2 minus 4 plus 4 minus 8 plus 1. So 4 and 4 will get cancelled. Minus 5. Right? Are you with me?
Yes, sir.
Yes, sir.
Yes, sir.
So your f of 1, 2 would be minus 5. So let's mark this. Just, we want to keep track of these values. Okay. And then the next one is the boundaries. So let's try from the first boundary. That means x0. So you put x is equal to 0 over here. That means f0y. Right. So you put x is equal to 0. So put x is equal to 0. Y square minus 4y plus 1. So f dash, that's what? 2y minus 4 is equal to 0. So y is 2. So point is 0, 2. So that means 4 minus 8 plus 1. So this becomes what? Again, minus 3.
3. Yes, sir.
So f02 is minus 3. So let's mark this. So this is your x0, and one point is there, f00. Okay. This point is also there, f00. So you put f00. So you will be only left with 1. So let's mark this as well. So let's try to find out the behavior of the function along the second boundary, which is y is equal to 2. So f of x2, right? So you put y is equal to 2. Okay. So this becomes x 2x square minus 4x. And then you y2, that means 4 minus 8 plus 1. So this becomes what? 2x square minus 4x minus 3. Are you with me?
Yes, sir.
Yes,
sir.
So what is your f dash? 4x minus 4. Okay. So you keep f dash to be 0. That means 4x minus 4 is equal to 0. So that means x is your 1. So now you want to find out f12, which you have already calculated, however. But okay, you may cross check over here. So you have already got that f12 is equal to minus 5. You will again get the same value. So you put x is equal to 1 over here. This becomes 2 minus 4. 2 minus 4 plus 4 minus 8 plus 1. Okay. So this becomes what? Again, minus 5 आ गया?
Yes, sir.
Same आया ना? पहले भी यही मिला था. So that is, that is a kind of good, this is a good sign that we are getting same thing. Okay. So now next is, so you have one more point along y is equal to 2, that is 1, 2. But that 1, 2 is, we have already calculated it. So the last boundary is what? Y is equal to 2x. So third, let's say y is equal to 2x. So put y is equal to 2x over here. So again, f of x, 2x. Put y is equal to 2x. 2x square minus 4x. And then 2x whole square minus 4 times the 2x. 2x whole square minus 4 times the 2x plus 1. Right? Is it okay? Yes, tell me. Is it okay?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, 2x square minus 4x plus 4x square minus 8x plus 1. Right, so this becomes 6x square minus 12x plus 1. So now keep f dash is equal to 0. That means 12x minus 12 is equal to 0. So that means x is your 1. So if your x is 1, your y will be again 2. So again you will get the same point. So x is 1. So your y is 2. So again, you can directly put it even f1, 2. Again, you will get same value from here as well. So that becomes 2 minus 4 plus 4. 2 minus 4 plus 4. And the next is minus 8 plus 1. Minus 8 plus 1. So yes, you will get the same thing, minus 5. So now, can you track the maxima and the minima? See, this is
Yes.
minus 5. This is minus 3, minus 5. So what is your maxima? That is
1.
1
1.
1.
What is your minima? Minus 5.
minus
5.
5.
Therefore, point of maxima is 0, 0. And maximum value कितनी आई?
1
1.
And point of minima?
1 2.
Yes. And कितनी आई minimum value? That's it.
minus 5.
ठीक है? So that's it for today.